by anti-chain labeling. Thanks.
Great. Thank you very much. Thanks especially to the organizers for putting this on and for inviting me. I'm really sorry that I can't be there because BLAST is always an amazing conference. But I often find that I have scheduling problems with BLAST and I wind up somewhere else, somewhere less fun. In any case, today, I would like to talk a little bit about the representation theory of residuated lattices. The main portion of what I'll discuss today is joint work with Peter Gibson, but I'll also mix in some joint work with William Zuluaga and some other projects along the same theme. So I would like to just dive right into this. I know that BLAST is a venue for algebraists essentially, and perhaps there's less logical interest, but I think for me the correct place to start with is a little bit of modal logic, and I hope you'll bear with me through some of this conceptual discussion at the beginning. So the talk will be in 3 parts, and I hope that everyone in the audience will at least be able to follow the first part. I'd like to first lay out some of the background on anti-chain labelings and POSET products, and really for me, this starts with modal logic, and I'd like to kind of discuss this conceptual foundation. Off we go. I think probably everybody in the room knows a little bit about intuitionistic logic and maybe a little bit about the semantics of intuitionistic logic. The semantics really comes, or the most popular semantics I might say, comes from what we call intuitionistic crypty frames, which is a fancy term for just POSETs, and intuitionistic crypty frames of POSET. But it's the way we think about it that counts. So an intuitionistic frame is a POSET, and we think of the elements of the POSET as possible worlds, or maybe if you're in a more prosaic state of mind, you think of them as situations or alternative states. The difference between this setup and classical logic is where we evaluate the truth or falsity of each proposition a set of worlds might say. So what I was saying is that most of the connectives of intuitionistic logic are evaluated locally at each world. This includes the conjunction and disjunction. The difference is that the material implication is swapped out by some kind of strict implication in intuitionistic logic. Here we read the proposition phi implies C as being true at a given world X if the material implication, the corresponding one, holds for each of the successors of X, every Y greater than X. A key condition involved in this is so-called persistency. I want it to be the case that if phi is true at a given world X, then it remains true for every Y greater than X in the POSET. I think of these as alternative states, and if something is true, then I expect it to keep being true in alternatives. This is kind of a magician's way of saying something which might be more mathematically elegantly stated as saying the set of points at which phi is true is an upset of the POSET. So the upsets of any POSET, if I think about these as an algebraic structure in their own right, they are a lattice and they satisfy the frame law. And hence in particular, they form a complete hiding algebra. In fact, it's well known that every complete hiding algebra embeds in the algebra of upsets of the POSETs of its prime filters. This upsets of the POSET of prime filters is sometimes called the canonical extension of the hiding algebra, the canonical completion. So a different perspective on all this setup that I've just given is that I can swap out these upsets for their characteristic functions. I can view their characteristic functions instead from the underlying set of the POSET, just to the doubleton set 0, 1. And here I think about these as monotone functions, perhaps from the POSET x less than or equal to the 2-element Boolean algebra. 2-element Boolean algebra here serves as an algebra of truth values. And what I've just described is the core idea of anti-chain labelings, which is what I would really like to get at today. What I've done is I've described a way of representing hiding algebras in this case as certain algebras consisting of some very concrete combinatorially simple functions, and these functions are examples of anti-chain labelings. All of this is in line with generally the representation theory that we see in classical algebra, for example, in terms of representing groups in terms of permutations, matrices, etc., or for Boolean algebras where we might think about representing those as continuous functions. So maybe motivated by many valued logics, we might instead think about worlds as being valued not just in the crisp truth values of 0 and 1, but in some kind of intermediate truth values, maybe half-truths, truths that are somehow that lie in between strictly crisp true and strictly crisp false. If you're familiar with MV algebras and the theory of Lukasiewicz logic, you might think about that as being conceptual background here. And there are lots of applications to this kind of fuzzy frame-based logic in the literature. It's not really clear at this stage in the state of the art what the correct way to do all of this kind of fuzzy modal logic stuff is. And I'll try to gesture at one way that makes sense because it's grounded in representation theory. One point about this, however, though, is that it's no longer enough to simply take monotone functions. I can't simply take monotone functions and expect to be able to get a rich representation. I have to take something slightly more elegant. Throughout this talk, I would like to think about two themes kind of interlaced together. I'd like to think about logic and representation theories guiding each other. In particular, we consider generalizations of frames, and these lead us to more rich representation theories. And on the other hand, we think about representation theory as guiding us to seeing the correct generalization of persistency, monotonicity, and these kinds of things that come from intuitionistic logic. So to get into a little bit more of the technical meat of what I would like to discuss, first I'll give you the definition of residuated lattices. Probably many people in the audience already know this, but a residuated lattice is some kind of algebraic structure, an ordered algebraic structure. In my particular parlance here, I'll use residuated lattices to mean bounded commutative integral residuated lattices. And I don't want to repeat all of these adjectives all the time. What that means more formally is that I take one reduct that's a bounded lattice. I take another reduct that is a commutative monoid, where the monoid unit is the top element of the lattice. And these two structures are linked together by this residuation law. To wit, if I take x, y, and z in the algebra A, then I have x times y is smaller than z, if and only if x is smaller than y implies z. Implies is this additional residual operation in the signature that I haven't used yet. Usually, as we do throughout this kinds of algebraic study, I'll use juxtaposition and just write xy for x times y. Something to note, if you're a logician following along, is that residuated lattices give the equivalent algebraic semantic for extensions of the full lambic calculus, here formulated with exchange, weakening, and falsum. Something implicit in what I just said is that we drop the contraction rule from the intuitionistic sequent calculus LJ. So I'm thinking about taking the calculus for intuitionistic logic and getting rid of some of the typical rules. Here, this product operation involved in the residuation law interprets the comma of proof theory. So I should think about this, this product operation as being some kind of a conjunction. And there are lots and lots of familiar examples of residuated lattices. If I had not included some of these adjectives like bounded and commutative and so forth, you might think about lattice ordered groups and so forth. But in the narrower sense that I mean residuated lattices, it's still quite rich. I include in this definition, for example, hiding algebras and Boolean algebras, which I think everyone knows. I include also MTL algebras. These are the algebraic semantics of T-norm-based logics. They are precisely residuated lattices in the variety generated by the totally ordered residuated lattices. For that reason, they're studied quite a lot. They're linked to fuzzy logics. I might think about so-called GBL algebras, which satisfy the divisibility condition, namely that x times x implies y is x meet y. This comes from also the study of lattice-ordered groups, where I think about some kind of notions of cancelativity and divisibility as being important. More special than GBL algebras, I might think about BL algebras. And these are the algebraic semantics of Peter Hayek's basic fuzzy logic. This is the intersection of MTL and GBL. MB algebras, I think people are also familiar with. This is the algebraic semantics of Lukasiewicz logic. They're BL algebras that satisfy some kind of law of double negation, where the negation is x implies 0. Going back to hiding algebras, I might think about the Gödel algebras, which are just the linear or prelinear hiding algebras, the intersection of MTL and hiding algebras. Now, most of the results will not be phrased in this language, but I can make precise this idea of frames I was discussing. Maybe for the sake of catching up on the technical difficulties, I'll skip this. But you can make precise this notion of non-classical frames that I was alluding to just by thinking about worlds as being valued in residuated lattices, of which the two-element Boolean algebra is a particular example. Now I get to the meat of it. I would like to replace this notion of the persistency condition or monotone functions into the two-element Boolean algebra by something slightly more elegant that's still combinatorially simple. And sort of the main definition of this talk is as follows. If I take a poset, I will also take an index collection of residuated lattices. And for technical reasons, I'll assume that this index collection shares a common least element and a common greatest element. This is a collection that's labeled indexed by the poset itself. So an anti-chain labeling is simply a choice function in the full direct product that satisfies some compatibility condition with respect to the poset structure, with respect to the order that lies on this index set. And this is worth scrutinizing for a moment. The compatibility condition is as follows. If I take X to be strictly smaller than Y in the poset, this means either the function assumes the value 0 at X or it assumes the value 1 at Y. I'm using common values 0 and 1 for the bounds here. If you think about it, this is a generalization of the notion of being a monotone function into 0, 1 to the two-element Boolean algebra, but it's a generalization that's suitable for more rich ordered structures at each node. I'll give you an example here. Pictographically, I might think about this algebra AX as labeling each node. This is something you might think of as the three-element MV algebra, for example. It has 0 and 1, but also some intermediate value A. An example of an anti-chain labeling or an AC labeling is the first tree that I've labeled. This tree is a poset. I can label all the nodes down here by 0 and all the ones up top by 1. And according to this condition, if I think about it, I can label an A right on this node. I'm allowed to do that. Contrast this against the one on the right, where I've labeled the bottom node by A as well. I'm not allowed to do this because it doesn't satisfy this compatibility condition. A different way, and perhaps an intuitive way of thinking about this, is that all of the elements in the support, that is the elements that are not 0 or 1, these must form an anti-chain in the way that I create the labeled acid diagram with this poset. Now, getting to the more algebraic content of anti-chain labelings, because I'm interested in representing algebras as some kind of algebras of anti-chain labelings, I might take the same setup where I take a poset and index collection of residuated lattices. Same thing, common least element, common greatest element. We'll take B to be the set of all the anti-chain labelings over this setup. And I'll define a bunch of operations on B as follows. First of all, I define the operations meet, join, product, and the null array operations 0 and 1 pointwise. They're defined exactly as in the direct product. The only difference, as if you think back to the frames we started off discussing, the only difference is the implication operation, which is defined in this kind of fuzzy way, this kind of funny way, where F implies G if I evaluated at X. Well, it's evaluated locally at X, the implication at the particular node X, the algebra labeling that, if for all Y strictly greater than X, F of Y is smaller in the order locally than G of Y. And otherwise, I shoot the thing down to 0. So I modify the original implications that appear at each node in this kind of way, which a priori looks a little bit strange. But this works out to be the correct thing. So the algebra B with these operations is called the poset product. The product is the algebra of anti-chain labelings in this sense. And a fact that isn't too hard to prove is that a poset product of poset index family of residuated lattices is again a residuated lattice. Residuated lattices are closed under this kind of complicated construction. A simpler way to present it that I prefer involves the notion of nuclei, conuclei. So if I take a residuated lattice, I take a map on the residuated lattice. I will call this map a conucleus if, first of all, the map is an interior operator. That's the first 3 conditions here. And secondly, the map satisfies this kind of hemimorphism condition where sigma of x times sigma of y is smaller than sigma of xy. It's not quite a multiplicative homomorphism, but it has kind of half of this. And additionally, for technical conditions, I assume that sigma of x times sigma of 1 is sigma of 1 times sigma of x is just sigma of x. Sigma of 1 acts as an identity. So if I assume these things, I stipulate these things for the map sigma, then sigma, and I take the image of the underlying residuated lattice, I get a residuated lattice again. The only thing I need to do in order to get a residuated lattice back from taking the image is I need to modify the original meet operation by making sure that it's closed under sigma. So I postfix by sigma in that case, and I do the same with the implication operation. If I do these two things, the image of a residuated lattice under a conucleus is a residuated lattice again. Now, if I go back to my setup from before, I take a poset and an index collection of residuated lattices, same common elements. I take B to be the full direct product of this index family, and I define a map. I'll call it box because of the connection to modal logic, which I would like to kind of stalk throughout this talk, but I'll call it box. And I'll define box in sort of this weird way. I'll say that box of a choice function f evaluated at x is just f of x if f of y is equal to 1 for all the strict successors of x. And otherwise, just as in the definition of implication I gave you before, I shoot it down to 0. It turns out that box, if I define it in this way on the direct product, is always a conucleus. And the conuclear image under this particular interior operator coincides with the poset product. And this is a nicer way to think about poset products, I think, because first of all, it gives you an instant proof, for example, that the poset product of residuated lattices is a residuated lattice. Here are several different kind of alternative descriptions of what anti-chain labelings are. I think most of them are quite obvious if you understand a little bit about interior operators or conuclei. What it more or less says is that the anti-chain labelings are the fixed points under box, however you take that. Perhaps the most interesting piece is part 4, where if I take an anti-chain labeling, I can really split it into 3 parts. And I saw that in the diagram before. I could think about the part that assumes the value 1. I can think about the part that assumes the value 0. The part that assumes the value 1 is an upset. The part that assumes the value 0 is a downset. And what's left over has to be an anti-chain, hence the name anti-chain labelings. And if I define any kind of labeling of a Hasse diagram in this way, this is also an anti-chain labeling in the same sense. So all of these are equivalent notions. Now, how do I think about poset products intuitively? I've kind of laid out some stuff, some of which is a little bit technical. This stuff was originally introduced by Peter Gibson and Franco Montagna, and I think what they were trying to go for is to find some kind of common generalization of the notion of a direct product, which we use throughout universal algebra, and the notion of nested sums, which are some kinds called ordinal sums in MTL algebras or BL algebras, for example. And how does it generalize these two things? Well, first of all, one point that I would like to make is if I take a poset and it's discretely ordered, then the poset product, as I've described it, is simply the direct product. Poset product by a discretely ordered poset is the direct product. Now, on the other hand, if I take a 2-element poset, so the elements are x, y with x strictly smaller than y, then the poset product consists of the nested sums of the algebras at each node. So intuitively, I get this nested sum idea by replacing the unit of the first one by the second algebra. So I just drop in a new algebra where the previous one used to be. So poset products, you can think about constructing them by iterating the notion of a direct product and iterating with the nested sum construction. Maybe I do direct product for a while, then nested sum, and then go back to direct product and so forth and so on. That's what poset products are. Now there's a lot of stuff in the literature already about poset product representations, representing different kinds of algebras as algebras of anti-chain labelings. So I'd like to recall from before that a GBL algebra is a residuated lattice that satisfies the divisibility law. X times X implies Y is X mu Y. Almost all of the past work in the literature on poset product representations is directed at GBL algebras or at BL algebras, which are special GBL algebras. They're the totally ordered GBL algebras and the variety generated by the totally ordered ones. And probably before the work that I'll report on today, the state of the art on this comes from maybe the work of Gibson and Montagna around 2010. And there are some very nice embedding results for GBL algebras. In particular, they prove that every GBL algebra embeds into a coset product of totally ordered MB algebras as a first point. And if I assume furthermore that the GBL algebra is n-potent, that means it satisfies the identity x to the n plus 1 is equal to x to the n, generalizing idempotence. Then I can do better. I can get this to embed into a coset product of finite simple n-potent MB algebra chains. Now, finite simple n-potent MB algebra chains are not quite as simple as the two-element Boolean algebra, but they're still incredibly simple combinatorial objects, and we have a good handle on them. Even arbitrary totally ordered MV algebras are dramatically simpler than GBL algebras. So in some sense, these kinds of embedding results represent a tremendous reduction in complexity from the algebras we start with to algebras that we have a much better combinatorial handle on. And there are a lot of consequences of this kind of representation theory. There's decidability even for the universal theory of GBL due to Gibson and Montagna. Later on, this was used to do some amalgamation work for some subvarieties of GBL. You can find this in some of the work of Metcalfe, Montagna, and Sigmakis, etc. Lots of different applications for this work. So now I would like to kind of move past the introduction and get to the new contributions, some of the technical meat of what's going on. And I want to talk about representations beyond this divisibility property, because as I said, almost all the work so far has been on residuated lattices that enjoy divisibility. And one thing I'll try to convince you of today is that divisibility is really irrelevant to the matter. Divisibility may give us some of the properties that we need, but we can get nice representations in the complete absence of it as well. So how do we get coset product representations for non-divisible residuated lattices? Well, one point that I would like to make as before is that the representations are at their most useful when all the factors have a much lower complexity than the algebras we're interested in. The best possible case is if we focus on simple factors. Simple algebras are the ones where the congruences are the trivial ones, just the bottom congruence and the top congruence. And for residuated lattices, within the sense that I mean them, the simple residuated lattices have a nice characterization due to Kowalski and Ono way back in 2000. So if I take a simple residuated lattice and I take an element A of this simple residuated lattice, and as long as it's not the multiplicative identity, there exists some natural number n such that a to the power n is equal to 0. So I can annihilate elements in simple residuated lattices. So simple residuated lattices are in particular something that I will call multipotent. For each A, there exists an n and n such that this property holds. And something that is important is that this highlights the role of idempotent elements in coset product representations by simple residuated lattices. This says simple residuated lattices have no non-trivial idempotence, and therefore we expect the structure of idempotence to play a big role in the decomposition in terms of anti-chain labelings if we can get such representations. So let me get to some kind of technical definitions which we'll need in describing the structure of the idempotence and how they fit together for the representations I'll go for. So first, I will say that the idempotent center of a residuated lattice is just the collection of all the idempotent elements. This does not have to be a subalgebra. It doesn't have to be closed under meet or implication or anything like that. But when H of A is a subalgebra, it is necessarily a hiding subalgebra because it's an integral idempotent residuated lattice, and these are all hiding algebras. And in this case, I will say that if it's a subalgebra, and for every element in this subalgebra and for every element of the algebra, I have that the product of these two elements is the meet, I'll say that this is a central subalgebra of the residuated lattice A. So central subalgebra means subalgebra plus this condition that the products from inside and outside are equal to the meet. So this is the notion of a central subalgebra. So I'd also like to introduce a little bit about filters. Filters in residuated lattices, just as in hiding algebras, correspond to congruences, and we'll use this fact quite extensively. A filter of a residuated lattice, however, is a subset that's upward closed and not just closed under the meet, but also closed under the product. This does, however, entail that it's also closed under the meet. Now, for each subset of a residuated lattice, there's always a smallest filter containing this subset, and that's the filter generated by it, as you usually have in universal algebraic theories. A filter I will call central if it's the filter generated by the idempotent elements it contains. So if a filter is the smallest filter that contains the set of idempotents that it contains, then I'll say that it's central. And a value coming from the theory of lattice ordered groups here is simply a filter that's completely meet irreducible in the lattice of filters. So these are just some basic notions related to filters and centrality that I'll need in the sequel here. Now, I'll come here to sort of the fundamental notion of the talk, the fundamental new idea that I'll present. It depends, the representations by poset products, by anti-chain labelings, at least if we're restricting our attention to simple factors, this depends a lot on how this idempotent center H of A fits inside the algebra A. In general, this idempotent center could fit into a residuated lattice in a very ugly way that doesn't allow us to obtain any kind of representation in terms of poset products. But fortunately, we can isolate the appropriate conditions that allow us to tangle out the simple factors from a residuated lattice and decompose it in terms of a poset product and get a nice representation theory. And the crucial notion is the following definition of centered residuated lattices. So a residuated lattice A is called centered if, first of all, its idempotent center is a central subalgebra. 2, every filter of the residuated lattice is a central filter. And third, somewhat technically, I'll give you a picture in a moment, but somewhat technically, A satisfies something I'll call the squared condition. If I take an idempotent element I and an arbitrary element A, then there exists another idempotent element J, so that I meet J is smaller than A is smaller than I join J. So A gets trapped between these two idempotent elements. And the theorem we're going for today is the following, which is part of ongoing work with Peter Gibson, that every centered residuated lattice embeds into a poset product of simple residuated lattices and is therefore isomorphic to an algebra of anti-chain labelings. This gets at the kind of representation theory we want. So I would like to comment a little bit briefly about just a couple of these notions in the definition of centered residuated lattices. First of all, remember what multipotent means. Multipotent means that there exists some integer so that you multiply A by itself that many times and it stabilizes. Not quite idempotent, but a generalization of this. It turns out you can give a quite transparent description of every filter being central in terms of multipotence. They turn out to be the same notion. And I think that this lemma, as I've displayed it, I think 2 implies 1 is quite easy to prove because you simply, if you take a filter, it's closed under multiplication. So if you take a filter and you just multiply everything, raise it to a high power, clearly you get a bunch of idempotents that determine the filter. But the converse might be a little bit surprising. And so I've given you a brief proof here. So if I take an element A and I take X to be the filter generated by this element, then by assumption, this filter is generated by the idempotence it contains. So there exists some idempotent element I that's below this element A, and this idempotent is in the filter. On the other hand, because the filter is generated by A, there exists some natural number n, so that A to the n is smaller than I, just based on what it means to be generated by a filter. And this means that I is equal to A to the n, and it follows directly from this just by doing a couple of calculations that A to the n plus 1 has to be equal to A to the n. So multipotence is equivalent to every filter being central. You can think about these alternatively, and it's quite useful to think about one or the other in different contexts. Now, moving from this principle about every filter being central, I'd like to move to this mysterious square condition that's part of the definition of centered residuated lattices. So I flash the square condition back up there. I think it's much easier to understand if you look at this kind of picture. So here I have this element A that's an arbitrary element of the algebra floating around, and I take some element I that's an idempotent. It could be anywhere. The idea is that whenever I have such a configuration, I can trap A in this kind of idempotent square. The median joins, because the idempotents form a subalgebra, these will be idempotent elements as well. So I can trap A in this kind of square of idempotent elements. And this is a crucial piece of being able to get nice representations, having this grid of idempotents that parameterizes the algebra. Now, an important lemma for our kind of representation theory that we're going for is something called the Bloch-Ferraro theorem. This was first studied in the context of hoops and later in GBL algebras by Bloch and Ferraro and then Gibson and Montagna. And it's a description of the subdirectly irreducible members of these kinds of classes. Roughly speaking, what it says is the subdirectly irreducibles can be decomposed as some kind of nested or ordinal sums. And the top part of this nested or ordinal sum is some kind of linearly ordered algebra. So it's a very nice description of subdirectly irreducibles, and it mimics the description of congruences in hiding algebras, where a subdirectly irreducible hiding algebra, recall, is just simply one with a greatest element not equal to the identity element. So when all the filters are central, as we have in centered residuated lattices, then we can give a very nice form of the Bloch-Ferraro theorem. This is because of the square condition. In particular, I've stated that here. If I take A to be a subdirectly irreducible centered residuated lattice, then in particular, there's a maximum idempotent different from the identity. And this maximum idempotent splits the algebra. So for every element little a, I either have this maximal idempotent m is smaller than little a, or a is smaller than little m. There's a place where the algebra pinches off if it's subdirectly irreducible, and it lets us cut the algebra up into two pieces. This is an important aspect of the decomposition. I can give you a proof of this Bloch-Ferraro theorem briefly. It follows very easily by the square condition. So if I take a subdirectly irreducible algebra, it follows that the idempotent center is also a subdirectly irreducible algebra because all the filters are central. This means in particular that there's a unique subcover M of the idempotent center because it's a hiding algebra. Now, clearly M is the maximum element of the idempotent elements different from 1. I can apply the square condition here. If I take an element A, I apply the square condition, and there should exist an idempotent element J such that M meet J is smaller than A, which is smaller than M join J. Now, because of the way I've chosen M, I must either have that J is equal to 1 or J is smaller than M. In either case, I can see that A must be comparable to M, and that gives the result. Now, with these kinds of ingredients and lemmas together, I would like to sketch the main result of this embedding theorem. The proof involves a lot of technicalities, but I think conceptually it's now kind of clear what's going on. And you can proceed to do the embedding along the following steps. There are 4 steps. So if I'd like A to be a centered residuated lattice, we'll take A and we'll try to embed it in a poset product of simple residuated lattices. So first off, step 1, I take the collection of values of A ordered under inclusion. This is going to be the index poset of our poset product decomposition. Because all the elements of A all the filters are central, the lattice of filters of A is isomorphic to the lattice of filters of the idempotent center. And we could also just as well take the filters of the idempotent center values. Now for step 2, if I take a particular value and mod out by it, this turns out to be subdirectly irreducible for general principles because values are completely irreducible congruences. It's not hard to show from that. It's not hard to show, in fact, that the class of centered residuated lattices is closed under quotients. So if I take A and I mod out by this value X, and then I get a subdirectly irreducible centered residuated lattice, in fact. Now moving on to step 3, because I have a bunch of subdirectly irreducible centered residuated lattices, which I get by modding out all the values, for each of them, there exists some idempotent element, say M sub little x, And this is a splitting element coming from the Bloch-Ferrand theorem. For each of these, I could define the set A sub x to be the upset of this element, little m sub x. It turns out that this A sub x is well, it's not a full subalgebra, but it's the universe of a zero-free subalgebra. And so it forms a residuated lattice in its own right, swapping out the old zero by the m sub x. Now, as a final step, now that I've constructed both the index poset and all of the factors, the final step is to exhibit the embedding. So I form the poset product as I described it before. And the embedding is given by the following. I take an element A of my algebra A, and I send it to the choice function, which I'll denote by bracket A. And the way this acts on an element X in the index poset X is as follows. If this is an element in the algebra A sub X, then I just take the quotient. I take A mod X. Otherwise, I take it to be 0. The proof that this map that sends A to this bracket A is an embedding depends on a couple of technicalities. In particular, it depends on the fact that the idempotent center is a fully central subalgebra, together with A being a multipotent algebra, equivalently that all the filters are central. You have to do some technical finagling to get that this is an embedding, but it works out if you do this. All right, so this is the way the embedding theorem goes. And what I've done there is I've represented some class of residuated lattices. Every member of some class is an algebra of, every member of this class is an algebra of antichain labelings. But it might not be exactly what we want, because in logic, certainly I'm interested in equational classes of algebras. I'm not interested in any kind of class of algebras whatsoever. And centered residuated lattices I presented here is not even an elementary class. Multipotence, for example, is not something that's first order expressible. So it's a fairly bad class for many purposes. But there are lots of varieties that sit inside the class of centered residuated lattices. And I can give you several of them. You could come up with more of your own, I'm sure. But these are just some convenient natural varieties that sit inside the class of centered residuated lattices. So for every natural number n, I will define two such varieties. First, I'll define S sub n to be the subvariety of residuated lattices axiomatized by these three identities. First, if I take A sub n, this is an idempotent element according to this first identity, by the way. If I take A sub n, I multiply by B sub b, that's equal to the meet. That's A sub n meet b. This says in particular that the algebra is n-potent. The second identity says that implication, the idempotents are closed under implication. And the third condition is something that gives me the square condition for this class of algebras. So simply by firing the previous embedding theorem, I can get the members of S sub n embedded into poset products. Now, if I further stipulate another identity, I get a variety Cn. This identity involving these nested implications will turn out to express something to do with linearity of the factors. So for every natural number n, I get these two varieties, which are quite natural and have sort of natural descriptions. Now, the classic theorem about embedding theorems, about generation of varieties by poset products might be from this Gibson-Montagna 2010 paper. For every natural number n, the variety generated by poset products of simple n-potent MV algebras chains is the variety of n-potent GBL algebras. So it's not merely the case that I have an embedding theorem, it's that I have generation of the variety by this class of special algebras due to the fact that certain conditions are preserved. For example, divisibility is preserved when they're taking poset products. We can now upgrade that with the following theorem. If I take, again, an arbitrary natural number, then the variety Sn is the variety generated by poset products of simple n-potent residuated lattices. And the variety Cn is the variety generated by poset products of simple n-potent MTL algebras. These are chains, by the way, MTL algebra chains. Something that maybe is not obvious, but which I'll point out to you, is that both of these are generalizations of the GBL algebra case, because simple n-potent MV algebra chains are indeed simple n-potent MTL algebra chains. So here we have a nested hierarchy of different representation theorems and varieties they generate. Now, briefly, I'd like to talk a little bit about applications. The applications of this kind of representation theory are all over the place. And you can do many different things as you can with all kinds of concrete representation theories. But I'll just sketch a couple of things. So one thing that we discuss quite a lot is that representations by anti-chain labelings can be interpreted as Kripke type semantics for substructural logics. So all the theorems I just gave you in the last few slides immediately give Kripke style semantics for the logics corresponding to these varieties if you're a logically minded person. You can find all the details about doing that at full generality in a Studia Logica paper of mine from earlier this year. And I'll leave you to read that if you're interested. But there's also this kind of connection to modal logic that we've seen through this operator, this box operator, as I've called it. This is supposed to be a name for some kind of modal box. I'd like to outline a little bit about this modal connection in the Guy's Gödel, McKinsey, Tarski translations. And you can find more of the details of this because I won't be able to give you all the details, but you can find more of the details in a paper from last year of mine with William Zuloaga entitled Some Modal and Temporal Translations of Generalized Basic Logic. And I'll confine my discussion here to the GBL case because I think it's the most clear and perhaps it's the most interesting to you because it's connected to Vukoshevitz logic and MV algebras directly. But everything that I say can easily be applied to the case of SN or CN or whatever variety of centered residuated lattices may interest you. So what is this Gödel-McKinsey Tarski translation? Well, it connects intuitionistic logic, which is modeled by Hiding algebras, to classical modal logic, in particular the classical modal logic S4, which is modeled by interior algebras. The way it works is I recursively define a translation T. What I do is for every propositional variable P, the translation just prefixes P by a box. It leaves the constant 0 alone. And it also leaves alone the connectors conjunction and disjunction. What it does change, however, going back to the very first slide where we talked about changing implication, it changes implication. It takes the material implication, or it takes the intuitionistic implication, transforms it to the material implication, and prefixes it by a box. So you can think about intuitionistic implication as being box prefix material implication. And I can extend this to sets of formulas in the obvious way. What the translation says, I don't know the history of this, but it's due, I think, independently to each of Gödel, McKinsey, and Tarski. What the translation says is that a formula phi is provable from a set of formulas gamma in intuitionistic logic, if and only if the translation of phi is provable from the translation of gamma in this classical modal logic S4. Now, I can use the machinery of anti-chain labelings as I've laid it out to give some kind of fuzzy version of the Gödel-McKinsey-Tarski translation. I can give some algebraic models of these, which are direct generalizations of the algebraic models of S4 algebras. So we say that an algebra of this form is an S4 MV algebra, provided that this reduct is an MV algebra. Recall that that's a BL algebra that satisfies this kind of double negation law. And this additional operation that I add box is an interior operator and an endomorphism in the signature meet.01. So S4 MV algebras are generalizations of interior algebras, and the only difference is that box is assumed to preserve this product operation, which was absent in the classical case because it was just meet. So it really is a direct generalization of the S4 algebras that you might study if you were into Boolean algebras with operators or classical modal logic. Now, in the embedding theorem for GBL algebras, the poset product is a conuclear image of the direct product. Remember that I take some kind of direct product of the factors and I apply a conucleus to this. Well, the direct product of those factors in the GBL case is a family of finite simple MV algebra chains. Turns out the conucleus also satisfies the conditions of defining the box of an S4 MV algebra. So if I take this direct product and I add this box to it, that's an S4 MV algebra. And this is the fact that's kind of underlies the translation that I might have in this fuzzy case. The only thing I need to do additionally is extend the translation T that's already defined back in Gödel's day by stipulating that T respects the product. T is a homomorphism with respect to the product, so to speak. And with this, it's not hard to prove that if I look in the logics corresponding to GBL algebras and S4MV algebras, then gamma proves in the consequence relation of GBL the formula phi, if and only if the translations of the formula gamma proves in the logic S4MV the translation of this phi. And actually, you can do a lot of things along these lines. You can extend this to temporal modalities and so forth. But I will not belabor the point further. I just wanted to mention that these are the kinds of applications you can get at this, as well as the kind of applications to decidability and relational semantics that I alluded to before. So maybe very quickly in just 30 seconds, I'll talk about ongoing work in these directions. Kind of the obvious thing that we haven't seen here, but maybe sits around everywhere, is to add some topological content to what we've done. Because a lot of the things that I've done are transparently inspired by a Sakya duality for hiding algebras. And we would like to add some kind of topological content to get some kind of a Sakya duality for the substructural setting. However, this is dramatically trickier than you might at first believe. There are really a lot of complicated topological challenges involved in this. Another project that we're working on is to go beyond simple factors. There are also some kind of technical challenges in doing this, but we can get some more expressive representation theories out of this if we do so. And a particularly promising direction, I think, is to further develop this connection to modal logic, which is quite nice. And I think you can probably get a fully substructural block of Sakya type theory involving modal companions and really connect these modal substructural logics to the ones downstairs, the intuitionistic substructural logic, so to speak. So with that, I think my time is up. So I'll thank you for your attention.
Questions?
Sarah. I was wondering about this connection with modal logic because there's been some work about ongoing and the algebras with modalities. And I was wondering if you have looked at the connection of this approach with that for the algebras with the other expansions that are around.
I can't quite hear the question. Maybe there's a microphone or.
Can you hear me better? Can you hear me?
I can't hear.
Okay. I was wondering about if you have looked up the relations between the vector and the algebras with the other expansions and the algebra by modalities that are around. Because there has been some work on finding the right way to put a modality on the algebra. So this is quite nice, and I was wondering if you have already looked at the connections.
Yeah, of course, there's a sea of different notions of fuzzy modal logics out there these days. I don't know the literature well enough to compare this particular version that I'm presenting to the other ones that are out there. But certainly, I think that this is something worth doing and something that we will do as the modal aspect of the project progresses further. So it would be nice to tie these things together and perhaps get some kind of understanding of the hierarchy of fuzzy modal logics.
Yeah, I was thinking in particular about the work of Amanda and on these things, which may be very connecting very nicely with what you've done.
And my impression there is that they, in the work of Amanda, for example, they tend to add modal operators to chains already. And as soon as we add the modal operators in the setting I'm discussing, any notion of semi-linearity kind of goes out the window, much as it does in the classical setting. So I would guess that they turn out to be quite different, but I don't know for sure.
Yeah, very much. Thank you.
Other questions? Thanks.
Hi, so this co-nucleus that you talk about, and in the last couple slides, this translation, substructural translation that mirrors the Gödel translation. Am I right in thinking that's just a direct analog? This co-nucleus seems like what you might call a skeleton when you just look at a hiding algorithm. Is that pretty much a direct relationship?
Well, I think in my terminology, if I think about a hiding algebra and I think about its skeleton, I would think then about the image under the double negation of the hiding algebra. This is also a Boolean algebra, of course. But instead, I think that it's true, of course, that every hiding algebra is a conuclear image of some Boolean algebra. But the Boolean algebra that it's a conuclear image of is its free Boolean extension, its Booleanization, which you can add a modal box to. And this is a bigger Boolean algebra than the hiding algebra is. So I don't think it's really a skeletal notion. It's rather going the other way to a bigger Boolean algebra where conucleus lives on that. But it is directly analogous to that setup in the hiding algebra and the modal algebra case.
Cool. Yeah, that clears things up.
Other questions?
Do we have any questions from the online participants? If so, please just unmute yourself and speak up.
Don't seem to be the case.
So I had a question. You defined this central subalgebra somewhere around page 18 or so, making reference to idempotent. I was just curious, is there any relation with commutators or some classical notion of centrality of some algebras in here, or where did
I don't know the theory of central elements in universal algebra well enough to say. It's entirely possible that there is, and you can carry this forth and maybe in some more general setting. I think William Zulawaga has worked a little bit on this direction, but I don't know it very well.
All right. Oh. If there are no more questions here, then it seems to be the case. Let's thank the speaker again.